All right, now that we've kind of restricted our variables, we've sort of set parameters for what makes sense in this situation. Now we're going to try and go ahead and optimize our volume. We're trying to figure out what's the way that we can come up with lengths and widths and heights of this box in order to make our volume as big as possible. So we're using, I said in the first video, we're going to use derivatives. We're applying derivatives to real world situations. So think about how we've used derivatives in the past. We've used derivatives when we found our critical values. We could determine if our critical values were a maximum or a minimum. We could figure out where our function's increasing and decreasing, and that would help us determine where we had a maximum or a minimum. Well, that's like kind of what we're doing now. We're trying to figure out where can I have a maximum or a minimum. In this instance, we're trying to maximize volume. So we can use the derivative to help us find where do we have a maximum. So maximums and minimums occur at critical values. So I need to find my critical values. So to maximize volume, find the critical values of your volume function. So our volume function is V is 27x minus x to the third over 4, which is the same thing as 1/4 x to the third. Sorry, that looks really weird. Remember, it was x to the third over 4. I just created it into 1/4 x to the third. So now you might be saying like, oh, that's why Ms. Briscoe split that big fraction up into 2 separate terms, so that way it's easier to take the derivative. So I'm going to take the derivative, and remember, we'll just call it z prime. So derivative of volume is 27 minus, take the exponent, pull it out front, minus 3/4 x squared. So to find critical values, you just set your derivative equal to 0. So 0 equals 27 minus 3/4 x squared. Move my 3/4 x squared to the left side. Trying to get rid of my 3/4, so I multiply by the opposite reciprocal, 4/3, which gives me x squared equals 36. Oh man. So x is plus or minus 6. Remember, when you take the square root of a number, you have to do plus or minus. However, we set a reasonable domain earlier. And we said that it doesn't make any sense for the side lengths of our box to be negative. So -6 is outside of our domain. So we don't need to worry about it. So the only critical value we need to worry about is 6. So another blast, rewind back to a long time ago. We have a specific interval that we're looking at for our x value. It's in between 0 and the square root of 108. If you remember from a long time ago, when you're trying to find the maximum and minimum on a interval, remember you have to check what's the y value at your critical value, but then you also have to compare it to the y values of your endpoints of your interval. So we're going to plug 6, which is our critical value, 0 and square root of 108 into our original function. So we're actually plugging them into the volume function, not the derivative, the original volume function, which is 27x minus 1/4 x to the third. So when you plug in 0, you get 0, which makes sense. If your side length is 0, your volume is 0. If you plug in 6, that's 27 times 6 minus 1/4 6 cubed, which is 108. And then to find the volume at square root of 108, you do 27 minus square root of 108 minus 1/4 times the square root of 108 cubed, and that gives you 0. So you compare your y values and you have a maximum of 108. That's the biggest volume that we could come up with. So we maximize volume. Volume is maximized when x is 6. And if you remember from a long time ago, we found this equation for height. So if we know what x is, the length and width of our base, we can find out what height is. So you would plug 6 in here for x to find your height. So our height is 108 minus 6 squared over 4 times 6, which is 3. Whoa, sorry. So that means that the dimensions are 6 by 6 by 3. The length is 6, the width is 6, and the height is 3 inches. And that's how you maximize your volume. So in conclusion, let's kind of wrap up how you optimize problems. First, you want to obviously assign variables to all of your unknown quantities. So in this instance, it was length and width. Depending on our situation, it's going to be something else. You're going to write 2 equations. Your primary equation is what you're trying to optimize, like whatever you're trying to find the max or min for, whatever you're trying to maximize or minimize. Your secondary equation, there's going to be some other information given in your word problem, and the secondary equation is solely used for you to isolate one of the variables. So that way you can go plug it back into the primary equation. Remember, your primary equation will have 2 variables. You use your secondary equation to isolate one of those variables, and then you go plug it back into the primary equation. Make sure you determine a feasible domain for your primary equation, so like your sides can't be negative. Usually it's things like distances, amounts of time. Those things can't be negative. And then like in our last example, we could restrict the surface area a little bit. So determine your feasible domain. And then, remember, we're trying to maximize or minimize something, so we have to find critical values. So you take the derivative of your primary equation, and you find those critical values. Take your derivative, set it equal to 0, check where your derivative is undefined to find your critical values. And then remember, we're going to have a closed interval, so you're going to plug your critical values as well as the endpoints of your domain into your primary equation to find max or min. Sometimes we're not going to even worry about that. Like later on, we'll just like wherever your critical value is, like after we do enough problems, we'll see like, oh, wherever you find your critical value, that ends up being like where you have the max or min. So you can plug your critical value back into the original to get the corresponding y value. There you go.